Here we go. We're going to do a little introduction to binomial distributions today. So we're going to work through some of this and then we'll really get into it tomorrow. Right, so it says, in the 2005 Conference USA basketball tournament, Memphis trailed Louisville by 2 points at the buzzer. Memphis's Darius Washington attempted a three-pointer. He missed, but was fouled, and he went to the line for 3 free throws. Each made free throw is worth 1 point. Was it smart to foul? So, first, it says, what are all the possible ways the shots could fall? So what are the possible outcomes? He either makes it or he misses it. So there's 2 possible outcomes. And there's 3 of them. So it's going to be 2 raised to the 3rd power. So there's 8 different outcomes. Okay, so let's list those. So he could do make. Or he could do make, miss. And number 3, he could do make, miss. Or he could miss and make the next 2. And then 5, I had miss, make, miss. And then 6, I had miss, make. 7 was make, miss, make. And then number 8, what was number 8? He missed all of them. Miss. All right, so it says he was a 72% free throw shooter. Find the probability that Memphis will win, they will lose, or they will go to overtime. When you have found the probabilities, put them in the table in number 3. Okay, so in order for them to win, he would have to make all 3. Correct? We're going to assume for these purposes that the shots are independent of each other. Okay, so the probability that they win, it would be 0.72. He would have to make all 3 of them. So it would be 0.72 raised to the 3rd power. So take your calculator and write down that probability. And what is that? 0.373. So now let's find the probability that he loses, that the team loses. All right. So there's 2 different outcomes where they lose. First, he misses all 3 shots. And so what is that probability? Well, it's the complement of making them, right? So it would be 1 minus 0.72, which would give me 0.28. And so then we're going to do 0.28 raised to the 3rd power. Miss. And what is that probability? 0.02. Okay, it's pretty low if he's a 72% free throw shooter, right? So 0.022. But also they're going to lose if he only makes 1 of the free throws, right? So we could do 1 make and 2 misses. And so that probability would be 0.72, he makes it, times 0.28 raised to the 2nd power. He misses 2. And how many different ways are there where he makes 1 and misses 2? Let's see, there's 1, 2, and 3. 3 different ways. So I'm going to do 0.72 times 0.28 raised to the 2nd power, and then multiply that times 3. Okay, so put that into your calculator. And we get
169.
Okay. That's what I got. And the last outcome, they go to overtime. All right, so 2 makes and 1 miss. All right, so that's going to be 0.72 raised to the second power times the probability that he misses 1, so that would be 0.28. And how many different combinations where he makes 2 and misses 1? There's 1, 2, 3 also, so I'm gonna multiply that times 3. And so that gives me what? 0.435. Okay, so let's look at this chart here. Let's say that Memphis is down by 2 and there's 3 shots left. What is the probability that they win? That he makes all 3? We found that it was 0.373. What is the probability that they lose? Well, there's 2 different ways they lose, right? It was 0.169, or he misses all 3, 0.022. Those outcomes are mutually exclusive, so we can add them together. So we got 0.022 plus 0.169. That's going to give me 0.191. So about a 19% chance that they lose. And the probability that they go to overtime is going to be 0.435. We found that. So about a 37% chance they win, about a 19% chance that they lose, about a 44% chance that they tie and they go to overtime. Okay, well, let's look at another scenario here. Let's say he makes the first one. And there are 2 shots remaining. So what's the probability that they win? He would have to make the first and then make the second for them to win. So that's going to be 0.72 raised to the second power. And that probability, let's see, I got 0.518. What's the probability that they lose? He would have to miss the first and miss the second. So that would be 0.28 raised to the second power. And that probability is like, I got 0.079. And what's the probability that they go to overtime? He would have to make 1 more. So it could either be miss and then make, or make the shot and then he misses it. So that's going to be 0.28, he misses, times 0.72, he makes it. And there are 2 different ways to do that. So we're going to multiply that times 2. So 0.28 times 0.72 times 2, that's going to give us like 0.403. Okay, and let's look at this last one here. Let's say that he's made 1, but there's only 1 shot left. So he made 1 and he missed 1. So what's the probability that they win? It's 0. Okay, because he's already missed 1. What's the probability that they lose now? It's the probability that he misses the next shot, which would be 0.28. And what's the probability that they go to overtime? It's the probability that he makes the next shot, which would be 0.72. Okay. All right, well, let me go back here and write down, there's a formula. This is a type of distribution that we're gonna get to in just a second, all right? But it is n choose k. And then we have p raised to the k times 1 minus p. And then we have raised to the n minus k. And so let me fill in what these are. Okay, so this is the total shots. This k is the number of makes. This p raised to the k is the probability that he makes the shot. And this is the probability that he misses the shot. And so we're going to kind of, this is a formula for a binomial distribution, okay, which we're going to look at and kind of explore in just a second. But let's answer this last question here. Washington is a 40% three-point shooter. Do you think that it was smart to foul? Okay, so should they just let him shoot the three-pointer and see if he makes it? Well, if so, what's the probability that they win? It would be 0.4. What's the probability that they lose if they don't foul? Then it would be the complement of that, which would be 0.6. So I said, was it smart to foul? Maybe. And this is kind of artificial, right? Because there might be other factors. Are they playing at home? Where is he shooting from? You know, is he guarded, et cetera, et cetera, et cetera, right? But I said the chance of losing in regulation goes down. All right, the probability we found that they lose was 0.191. But they might have to go to overtime. And lose in overtime. Okay, and so we did that just to kind of set this up, all right? So let's talk about a binomial random variable. There are 4 criteria for a binomial random variable. And I have a little mnemonic device for remembering that. It is called BENS. And BEN stands for this. Okay, first, it must be binary. Meaning, there are 2 outcomes, and we define those outcomes as success or utter and abject failure. I'm a loser, baby. Okay, so in this case, he makes the shot, success. He misses the shot, failure. Okay, that's the first thing. Second thing, independent. all of the events must be independent. And so we were assuming, for our purposes of illustration here, that when he is shooting the free throws, that those 3 shots were independent of each other. Okay? Third one, and this is what makes it a binomial distribution as opposed to a geometric distribution, which we will look at a little later, is there is a fixed number of trials. And we denote that by n. Okay, and so this case, n was equal to 3. He was shooting 3 free throws. And the last one, we have the same probability for each trial. And in this case, it was the probability of success. We denote that by P. And it was equal to 72% in this case. So if these 4 criteria are met, then we can say that it is a binomial distribution. And we have a formula for the binomial distribution, which you will use on occasion. You probably need to be able to recognize it, but we will also use our calculator. Yes.
What's the difference between the independent and the same probability?
Well, 2 things can be independent of each other, but not have the same probability, right? So this is saying that, number 1, they must be independent. And then if they are independent, the probability for success must be the same for each trial. Does that make sense? But just because 2 things are independent of each other does not necessarily mean they have the same probability. And so to meet this criteria, they have to have the same probability. Yes?
Never mind.
Okay. Okay, so this is the formula. Probability that X equals K, where we have some outcome. So we have N choose K. We have the probability of success, P raised to the K. And then we have the probability of failure, 1 minus P. And this is raised to the N minus K. So again, let's define these. And here is the total. So in the previous example, it was the total number of shots. K is the number of successes. Okay, so this N choose K, that's a combination, right? So it's looking at the number of successes you could have out of the total. We'll look at an example in just a second. This is the probability of success. This is the probability of failure. And these 2 things must add to 1. Because they are complements of each other. Okay, so it says for each of the following situations, determine whether or not the given random variable has a binomial distribution, justify your answer. So we're going to go through the bins. Shuffle a deck of cards, turn over the top card, put the card back in the deck and shuffle again. Repeat this process 10 times. Let X equal the number of aces you observe. Okay, so is this binary? Yes, okay, we're going to define success. Is that we draw an ace. Failure would be not drawing an ace. Are these events independent? Yes, why? Because we put the card back, right? So we're gonna say independent. Independent. Because it's with replacement. Fixed number of trials. N is equal to 10 in this case, because I'm repeating the process 10 times. And the probability of success. How many aces are in a standard deck of cards? There will be 4 out of a total of 52. So yes, this is a binomial distribution. Okay, part B says choose 5 students at random from your class. Let Y equal the number who were over 6 feet tall. So there's this binary. We can say yes. Success is going to be greater than 6 feet tall. Failure is less than 6 feet tall. Was the selection independent? And so in this case, no, it was not because there was no replacement when I was selecting. So no replacement. And so if it fails any of the 4 criteria, then it is not binomial. So we say not binomial. Okay, so let me work this last problem here, the 2 parts, and then we'll take a quick little break. All right. So this says Pedro drives the same route to work on Monday through Friday. His route includes 1 traffic light. That's nice. According to the local traffic department, there's a 55% chance that the light will be red on a randomly selected workday. Suppose we choose 10 of Pedro's work days at random and let Y equal the number of times that the light is red. Explain why Y is a binomial random variable. Okay, so binary, we've got success. Okay, it's defined kind of strangely, but success we're defining as getting a red light. Failure would be not a red light. Are they independent? I would say so. Okay, if we're looking at different days, I think that is a reasonable assumption. So we can say yes. Fixed number of trials, N equals 10. And the probability of success in this case is 0.55. And so look at the next problem. It says find the probability that the light is red on exactly 7 days. So we're going to use our formula. We want the probability that Y is equal to 7. So there's 10 number of trials. We're going to do 10 choose 7 times the probability of success. Probability of success is 0.55 raised to the what? How many successes in this case? 7. So this is going to be 0.55 raised to the 7th power times probability of failure would be 0.45. 1 minus 0.55. And then this exponent would be the total n minus the number of successes. So there's 3 failures. Okay, and so let me show you how to calculate the combination on your calculator. So take your calculator, please. Hold on, let me. Sorry. I want this. It's right here. Okay, so we're going to go to menu, statistics, and then, oh, sorry, I made a mistake. That's the next one. Go to probability, and then we do combinations. And then we're going to put in 10, 7 and hit enter. And we are going to multiply that times 0.55. Oops, 0.55 raised to the 7th power. And then 0.45 raised to the 3rd power. And hit enter. And I did something wrong. So let me fix that. Okay, I forgot my exponent there. So it gives us that probability of exactly 7, which is 0.166. Okay, so that is one way you can use that formula, or this is another thing that we can do. We can do what is called binomial PDF. Okay, so let me show you that. Let's go to menu, statistics, and we go to distributions. And so we have used this before with the normal distribution, right? We have normal CDF, we have inverse normal. And then if you scroll down, there's a couple of binomials. Here we're going to use binomial PDF. So now it will ask us for the number of trials, which was 10. The probability of success was 0.55. And the X value here is going to be 7 because it asks for what's the probability that it is exactly 7. So let me put in 7 and we should get the same value there, 0.166. So let me go back to the notes here for just a second. So this was 0.166, or we're going to do binomial PDF, where we have 10 trials. Probability of success is 0.55. And then we're going to use PDF whenever it says what's the probability that it's exactly a certain outcome. So let me label these. Okay, this is number of trials. This is the probability. And it was 0.166. It says it is time for a pop quiz. I hope you're ready. Quiz consists of 5 multiple choice questions. Each question has 4 answer choices labeled A through D. So it's kind of like a stat says, you have no idea. Well, just take a wild guess. All right. We're going to let X equal the number of correct guesses. Is this a binomial setting? Well, let's go through. We have success equals we guess correctly. Failure, we're going to define as we guess incorrectly. Are they independent of each other? I think that's a reasonable assumption. Each answer we could say each answer does not affect the other. Fixed number of trials. Yes, there are 5 questions. And what is the probability of success? If we are guessing and there are 4, then it will be 0.25. Is it the same on every one? Yes. So this we can say is a binomial distribution because all 4 of these things are met. So 3 says calculate the probability of getting exactly 2 correct. Show your work. So let's do this the 2 ways. We have the probability that x is equal to 2. We're going to do 5 choose 2 times the probability of success, which is 0.25 raised to the second. Why is it raised to the second? Because I want to know the probability that I get exactly 2 right, times the probability that I get 3 of them wrong. So this would be 0.75 raised to the 3rd power. Okay, so take your calculator and calculate that, or we could do binomial PDF with 5 trials, probably a 0.25 and exactly 2. So calculate that probability for me, please. And somebody help me out. What we get? What is that? Okay, that's what I got. 0.264. 0.264. So there's about a 26% chance that you get 2 of them right. So let's fill in the table here on our probability distribution. That's 0.264. And let's go ahead and fill out the table. So take your calculator, do binomial PDF for 0, and then for 1, and then for 3, 4, and 5. Can someone help me out here with these probabilities? What's the probability they guess on all 5 and get none of them correct? 0.237. Don't go to Choctaw because you're pretty unlucky. What's the probability they get 1? Okay. 0.396, fairly high, right? Almost 40%. Probability that they get 3 right. 0.088 and 4. 0.015. And all 5 of them correct. Go out today and buy that lottery ticket because the probability of that happening is what? 0.0009. Okay. Question 5 says find and interpret the mean of the distribution. Okay. And so this is why I headed out the formula chart. Look at the formula chart. and find the distributions and look at the mean for a binomial distribution on the formula chart there. Anybody found it? This only works for a binomial distribution. What's the formula? N times P. Okay, if you think about it, that makes sense, right? If I'm a 72% free throw shooter, not like my illustrious basketball players in here, right? But if I shoot 100 free throws, then I should make 72 of them, okay, on average. And so I'm taking the total number and multiplying that by the probability. So what is the mean of this distribution? It's going to be 5 times 0.25. So that's going to be 1.25. So interpreting that after mini quizzes, the average number correct out of 5 is 1.25 questions. So now look at your formula chart. How do we find standard deviation of a binomial distribution? Sigma is the square root of, it's right next to the mean there, square root of what? Okay, so n times p is the mean, which was 1.25, times 1 minus p, which is the probability of failure. So times 0.75. So you put that into your calculator and we get 0.968. So interpreting that, the number correct on a quiz of 5 questions typically varies by 0.968 questions from the mean. Okay, and so we're going to look at one more thing here. It says, what is the probability of getting at most 3 correct? So we want the probability that X is less than or equal to 3. At most 3. So 0, 1, 2, or 3. And so since those outcomes are mutually exclusive, we can add them together. So we could add 0.237 plus 0.396 plus 0.264 plus 0.088. And if we do that, you should get 0.985. Or we could use what's called binomial CDF. So we use PDF if it's exactly one outcome. We use binomial cumulative distribution function, CDF, if it's like greater than or less than or more than 1. So we're going to do binomial CDF, 5 trials. Probability of success is 0.25. And then we do upper bound and lower bound. So in this case, my lower bound would be 0. My upper bound would be 3. And it's probably good practice to label these. So this is N, this is P, this is lower bound, this is upper bound. So take your calculator and go to binomial CDF and put in those values. And when I did that, I got 0.984, which is a little bit different from there due to some rounding errors there. That's fine. Okay, and so the last question here says, what is the probability of getting 3 or more correct? So we want the probability that X is greater than or equal to 3. And so if we're going off the table, we could add 3, 4, and 5. So 0.088 plus 0.015 plus 0.00 like 1. And there's about a 10% chance. Or we could do binomial CDF. N is 5. P is 0.25. My upper bound this time, excuse me, my lower bound would be 3. My upper bound would be 5. And if you put that into your calculator, I got 0.1035.